Is to record the meeting. Yeah. Okay. So once I have the recording will be posted up into here as well. So you guys can go back and look at what we talked about. In general today, I mean, and moving forward, I don't have a problem. If you guys have a question, you want to ask something, just unmute yourself when you have that question and then just ask away. That's fine with me. You can put it in the chat as well. But if I'd rather hear your voice if you guys are ready to do that. So just feel free to throw that out there. What I wanted to do real quick is talk about the syllabus, and I want to do that relatively quickly. You guys haven't had much of a chance to look it over yet. But I want to orient you with the stuff that you guys really care about, which is, how am I evaluated and assessed in this class? Okay. The name is a silly one, Analytical Foundations of Electrical and Computer Engineering. That's to say that it's basically a math course that is focused on kind of teaching you a little bit more about how to use this course. So Ashish, you're saying that you had an audio problem. Are anybody else having an audio issue?
No, I'm doing fine for the moment.
Okay.
My audio is good.
Okay. All right. If you're having, if you do have issues, just feel free to raise that up, and we'll try to address that. Real quick, I guess what I wanted.
I had the wrong speaker assigned, and I couldn't hear anybody. So maybe he needs to reassign where his audio is coming through within Zoom.
Okay, that's a new one on me. Reassigning the speaker. Okay. Well, Ashish, if you. Okay. Anyhow, well, the reason I picked on Ashish there is Ashish is also our TA for the course. Okay. So Ashish, can you maybe introduce yourself real quick?
Hi everybody, I am Ashish. I will be your TA for this course, and I'm looking forward to help you and work with you all during this new concept of teaching. I hope you have a good semester. Thank you.
So Ashish, maybe real quick, can you also maybe just what are you doing? You're a PhD student, and what are you focused on?
I'm working with Dr. Tauhan in wireless communication. I'm working on a project that is power project, and I'm working in the communications part, with underwater RF communication.
Underwater RF communications. Okay, so good. So a couple of things that he said there. He's working in power and RF communications, all of which are relatively important with the mathematical concepts that we'll introduce in this class. So we're going to talk about that and kind of motivate that a little bit here today. But real quick, there is a text required for the class. It is relatively inexpensive. If for whatever reason you really absolutely can't afford it, send me an email. You got my email there on the screen. We'll see what we can do. I want everyone to have access to that book. It's not the greatest. I will have notes for pretty much every class, or at least for every topic that we cover. And those notes will hopefully be helpful to you, and the text will help as well. Now, I guess kind of, moving forward, this class is about math and really about applications of math with respect to electrical and computer engineering. All right, so we're going to motivate that a little bit here today. Before I go into some of the real topics, because I will get into some real stuff today, a couple of things. So Ashish introduced himself there. One kind of nice thing about online stuff this semester is a lot of our grading will be handled automatically within Canvas. Okay, for homeworks, it will be handled automatically within Canvas. For grading of exams, I will do that. And so Ashish is going to be pretty freed up to really do some teaching. And so we are going to be having online office hours, both myself and Ashish, that we will be, essentially what I'm going to do is I'm going to send out to you guys a poll after this today. And that poll will basically have a couple of options that you can choose times that you would prefer to have office hours. So we'll have a couple of options basically so that we make sure that we choose times when you guys are not in class, okay? In addition, those office hours, some of them will be by me and some of them will be by Ashish. In addition, we probably are going to have an extra time, which will be sort of a recitation. We don't have an official recitation time for this class, but I'm going to have one evening session that you can come to, that Ashish will run, and it will be focused upon really kind of reinforcing some of the concepts, particularly stuff around MATLAB, which is the computing tool that we're going to use. Okay. All right. So that was a lot of material, but there'll be a summary announcement that comes out with that. So there'll be a poll coming to basically figure out when those office hours should be. We're going to have at least eight hours of office hours a week is my intention. My goal, this is a hard class for people because you're really getting into the content of what it means to be an electrical and computer engineer. But our intention, our hope is that as many of you, if you want to be successful, our intention is that you will be successful. So we want to have as much support for you guys as we go through this process as possible. Okay. So there'll be a summary announcement with that will come later. All right, the key thing, I'm going to skip over the topics and everything and kind of come back to that later. And I'm going to get to the stuff that you really care about, which is probably what is my grade going to be. And so there you have it there on the screen. So basically 70% of your grade is divided up between exams and projects. Okay, so there are 2 projects and 3 exams, and then 20% is the final exam. Okay, so 70% of your grade is split across those projects. So that tells you right there where to put your emphasis. The homework in this class, which is approximately weekly, is only about 8%. All right, so one question on the homework really isn't worth that much. All right, so don't stress about that too much. The goal of the homework is really to help you to learn the content. All right. In addition, you'll see I have this thing up here that says attendance at 2%, and I'm going to show you what that means here in a second, how I do it. The critical thing here probably is this piece. The final grade, I say, is never worse than the following. All right, so what do I mean by never worse than the following? So in other words, what that says, you look at that, an A is somewhere between 90 and 100. Well, what I might do is I might say that an A ranges from 100 to an 85, okay? People ask if I curve the course. I don't necessarily curve it, but what I do is I make a judgment call as to what an A is and what a B is and what a C is. So in other words, anyone with above a 70 will always have a C. Anyone above an 80 will always have a B. Anybody above a 90 will always have an A, but I might extend those ranges a little bit. All right, that's what I mean when I refer to that. All right. At the end of the semester, you know, if you're right on the borderline, and I think that you've shown a good improvement throughout the semester, for instance, I may bump you up a letter grade. All right. I never make it worse. In other words, I never say, well, that guy got a 90, but I think he was a slacker, so I'm just going to give him a B, right? I can't do that, but I will see if you're right at that edge, maybe I'll say, okay, well, I'll bump you up a little bit. Okay. Critical thing I want to talk about in this whole weird world that we're in right now is this whole thing right here about exams. Okay. So I'm going to do this the same way that I did it in the spring, and it seemed to work well for us in the spring. Okay. I did this with Dr. Yawu in 2112. Essentially what I have here is that I am going to post a PDF copy of the exam that is just like a PDF copy of the exam that I would give you if you were sitting in this classroom on the day of that exam, okay? That exam will be designed for you to be able to complete it in 75 minutes because that's what you have when you're in the classroom, okay?
Will we be using the lockdown browser?
Yeah, so let me go through that. So no lockdown browser, all right? Maybe I am being stupid and too easy, and you guys are going to cheat left and right. But as it says here, I am going to trust that you guys are adults. If I see you cheating on the first exam, things may change about this. But essentially what I'm saying is I am going to give you on the order of about probably, I need to think about this ultimately based on the exam. So we'll talk about this as the first date comes closer. But essentially probably 3 to 4 hours for you to be able to take that exam. Okay. And that is for everybody, whether, you know, if you have a disability services or something like that, you would get a potentially additional time as well. The intention is not for the exam to be longer, but the intention is for you to be able to take that PDF, print it, complete it, use your computer to answer questions, and scan it and resubmit it. I find that giving you additional time ensures that you will be able to complete everything comfortably. You have access to whatever, as it says here, you can use whatever resources you want other than other people in the class. All right. Or I should say other people. Okay. You can't talk to somebody who's taken the class before. You really can't talk to anybody else, but you can talk to the internet. You can use MATLAB. You can use the book. I am fine with that. I mean, in general, that's how real life works anyway. I don't usually just kind of sit around trying to come up with an idea if I know that I can find it online or something like that. Okay. So that will be done in the evening on the exam dates. I know that there will be logistical issues. Some of you will have some issues with that. In general, most of you won't. So we can deal with that. If you have an issue with that, you can take that up with me separately, and we can try to deal with that. I am not a fan of the lockdown browser. Maybe I should be, but my sense is that I want you to be comfortable, sit there, do the exam, and be successful. What I ask in return, I think I'm being pretty successful, or I think I'm being pretty
Lenient.
well, lenient. Yeah. So I'm being respectful, I think, of you guys. I'm trying to respect you as adult learners. You guys are adults. And it's scary to any of us to think about this, but you'll have a full-time job in 3 years. A lot of you guys, you know, doing really important things. And so I'm going to treat you like you're ready. You're on that pathway to do that. What I ask in return is that you respect me and you don't take advantage of that opportunity. To me, that whole lockdown browser thing seems like it would be incredibly stressful. And I think if I was, I don't think if I was a student, I would want to deal with it. I don't want to make you purchase a webcam if you don't have it, any of that kind of stuff. So anyway, there'll be logistical details for sure if we have that. But before I move on, because that's such a big topic, any questions about that?
I swear to you, I will not cheat through collaboration on anyone else with these tests.
Okay, welcome back, Nathan.
Quick question. So we need to have the textbook. When should we have the textbook? Because I ordered it, but it said it's going to be here, last week, but it says it's going to be here like a week and a half from now. So is it super necessary for the first week, or should I try to find a PDF of it online?
You should have it the first week. If you don't reach out to me. I don't think you'll find it essential, but it will be helpful in the first week.
Yeah, it's okay. Well, thank you, because it said it was Amazon Prime, but now it's saying it's going to be here September 21st. So.
Okay. All right. Any other questions about the grading or any of that stuff?
About the cutoff, when you said you would sometimes round people up, that decision I'm assuming is made at the end of the semester, right?
Oh yeah, it'll be on that last day when I make
Right.
that final decision. Now, I mean, the pathway will be one that is charted from the beginning of the semester. I'll give you an example. I had a student last year in this class that got a 13 on the first exam, and he got a 98 on the last exam. And I know he didn't cheat because he was sitting in front of me the whole time. That guy ended up right on the edge of passing and failing. And I basically said, I'm not going to fail somebody who's gone from a 13 to a 98. That's the kind of thing. I look at, since this is a math class, I guess I look at your derivative as well. I look to see if you're moving upward, then I'll give you that advantage, that type of thing.
Okay, thanks.
Mm-hmm. All right. The question, I expect there to be some detailed questions about the exams as we get to it. But I'll throw that out there for now. That's about all we've got for today.
Could you describe, how have students typically taken your exams? Because if you're saying we're free to use our resources except other people, it kind of gives the assumption that it's a crazy hard exam.
So,
okay, this is the exam. Oh my God.
Okay.
This is just an overview. We're not going to talk about the exam for the exam function.
So, you guys can mute yourself if you're not talking. That'll help. So, on the exams, I think what you'll find, I will give you a practice exam for the first one, so you kind of get a sense of what the content would look like. The intention is not that they would be crazy hard. The intention is that the exams should look like what you would have in a 75-minute period. So this will make a little bit more sense probably a week from today once we get into some real content. All right, but the first set of stuff is going to be on sine waves, and it's going to be on complex numbers and things like that. I'm going to expect you to show your work so I can see that you're working. But that's, I don't expect it to be crazy hard as you say. What I expect to see is that you show your work on those exams. I will be able to tell probably if you've cheated. That's should be fairly clear to me.
Sorry, crazy hard was the wrong way to describe it. I meant more so how challenging,
Crazy hard's a fair question. The goal always is that it's challenging, but that it's not threatening.
Gotcha.
How does that sound?
Yeah, that sounds good. Thank you.
Okay. All right. Now you may disagree with me after the first exam. We can have that discussion again, but we'll start there. I
guess we'll see.
You will see. Yeah. So you see that. So what I have here, these dates are approximately correct, the ones that are highlighted. What you see is that exam one is not. Exam one will be on October 1st. So it's kind of right after, I guess, what the official move-in date's going to be. We'll talk about that. I have my own expectations that we may never be face-to-face this semester, but we shall see how things play out on that front. Okay. I saw a question in the chat about the attendance here, so I'm going to get to that in a minute. Attendance is a very easy 2% to get, all right, if you come to class. And I'll show you how we do it here in a second. I have this thing in here about, and actually one more thing before I move on from the exam question here. And if I catch you guys doing chegg or talking to each other or whatever else, I'll go after you to the fullest extent that I can, right? I'm being pretty lenient, I think, for your own benefit, but I won't hesitate to go after it if I do catch it. All right. That's not to say that I'm going to look around trying to find it. I got better things to do than trying to find you guys cheat. All right. But if you do, I'm definitely going to go after it. All right. So we'll see how that proceeds. All right. But I did want to say that. One thing is in this class, I have this note here on calculators. All right. You guys are all really comfortable using the TI 9289, whatever. Those calculators are the same ones that I had. I wrote here in 1994. I got a TI 85. All right, no one can get a TI 85 anymore. They're more advanced versions of it, but not that much more advanced. In other words, that calculator, for lack of a better term, is just a piece of crap. As far as I'm concerned, it's a you guys have a computer that you walk around with in your pocket nowadays that can run far more powerful things, far cheaper than that calculator can. And, you know, as you go through real engineering, you don't see people use calculators all that often. Usually you're using some sort of Excel or MATLAB or Python is the new big thing, but you're using some sort of computer-based tool. So it, you know, ultimately it doesn't matter, but my suggestion to you and my focus is going to be in using MATLAB. Now, I always say that. Students always say, well, but when I come to the test, we don't have MATLAB. Well, that's different this year, okay? When you come to the test, you will have MATLAB because you'll have your computer nearby, okay? MATLAB is available on Mosaic, and it's also available for download for free on your computer from UNCC. And I didn't put up there a link to that, but maybe I should probably put it here real quick, and I'll send this out in an email, but software.uncc.edu, you can go there and you can download MATLAB. All right, it's very helpful to have on your machine. All right, I'm going to recommend that you get it for your own computer, and you'll use it not just here, but you'll use it in many classes after this one. Okay.
Quick question, sir.
Yep.
I was going through the MATLAB installer earlier today in preparation for this class, and I was wondering, is there a specific version of MATLAB that I should download? Just the newest version, or, you know, is there some, or whatever I choose? Does it matter?
You know, so you can get up to the newest version, which I think is R2020A.
Okay.
I don't see any reason to get anything older than the newest.
Okay. Well, thank you, sir.
Yep. Okay.
I also have a question too. This is more just in regards for exams or whatnot, but do you think we should be expecting to have any questions involving MATLAB where we have to simulate anything?
On an exam, no.
Okay. Just make
No,
sure.
so like I said with the exams should be exactly like what they would be like in the classroom.
Okay, that sounds good.
Yep. Okay. And I'll keep going here. All right. So in terms of other stuff here, so attendance is required. Okay. So let me see, how do I get out of this thing? So what I did is I created, and I will do this every time. What I have here is I will, every class period, I will put this in the chat. All right. So this is a Google form, and I sent this previously, but I will send it again.
I found this on the web.
And Google somehow recognized my voice from that. I don't know how. I must have said, okay, Google, and that made my phone wake up, and I did it a second time. Okay. All right. So what I just sent out, and I sent it to one person. All right. I just sent a link in the chat. You guys should all go to that link. You should all have access to it. If you don't, basically what I will typically do is you will go into this Google form, you put in your last name and your first name, submit it, and you will get credit for that class. There may or may not be a question that we also ask, which is relevant to the course material. All right, just a simple question that I ask. Most of the time, it'll just be your dates. So if you look at this, and this is all required for today, and I'll probably ask this question again on Thursday just to go at this. But I want everyone to take a stab at this. I put in through 2 questions that I want all of you guys to fill out, in addition to your last name and your first name, which is, first of all, why do you actually want to be an engineer? All right, I'm actually curious to know why you guys want to be engineers, because particularly with electrical and computer engineering, some of you guys might want to work for Duke Energy, and some of you guys might want to build, computers. All right, and there's a broad range of people, and I want to get a sense of, what's the thing that you're really passionate about, and what makes you want to be an engineer. You may think that's a hokey kind of question, and maybe it is. But I'm kind of curious. It actually helps me to kind of think a little bit about the class itself and the examples that I'll use. Okay. The other thing I put in there is to tell me an interesting fact about you. And I say that only because, like I said, I'm sitting in the classroom right now looking at a bunch of empty chairs, and I actually like to meet you guys in general. So you can put in the information there, and I can look at that. All right. So I know you guys have lots of questions on the exams and things like that. We'll get into those specific details as we get closer to it. I want to get into some real meat here today too. But fill out this form. The first thing I do in every lecture moving forward will be to post the day's link. All right. And then you will go in there and you will have to fill that out. Okay. All right. What am I leaving out? I hate this little bar. All right. What am I leaving out? Oh, I know what I'm leaving out. So interaction. I have this section here, if you guys can see it. I mentioned this thing called Discord. I really don't know what the hell it is, to be perfectly honest with you. I know you guys do. I kind of know what it is. I've read about it. I've heard about it. I know you guys use it. I created one. And several of you have already joined it. Because I'm an old man, I don't really know how to use it, as I said. There is a link to it here. If you click to that link, it should take you to something like this. This was me goofing around with it. What I'm looking for, I know you guys use this stuff, and I know that students use it a lot. I wanted to create one because I feel like this is a good way for us to be able to interact with each other. So if you guys have questions, I will monitor it, and you guys can ask me questions directly through it, and I can kind of monitor the conversations that you guys have. The question that I have about this is there anybody out there who's really good with this that can help me with it?
I am very familiar with Discord servers. I'm actually already moderating another one for a different class.
I literally run my own server.
Okay. So is Philip and Matthew were the two people I heard talking. So Philip.
I'm also relatively familiar with Discord.
Is that Josh?
Yes, sir, it is.
All right. I know a lot of you guys probably do that. So I'll start with Philip. You were the first one to speak up. Send me an email after this. And maybe you and I can catch up and you can help me.
Sounds like
all right. Sounds good.
All right. All right. So I want to utilize that. The other question I didn't mention here, you can feel free. I'm assuming that you guys are going to be able to reach out to me via Discord. So Philip, you can maybe educate me on that, but you'll be able to effectively send what amounts to a text message or email me. If you want to meet with me one-on-one, with questions at any time, normally, I'll let people come into my office. That obviously can't really happen right now. So if you want to meet with me, for now, I'd say email me or do whatever texting thing you do on Discord, I guess, to reach out to me. And we can set up a meeting. I like to meet with you guys. I don't want to be overly intimidating to you. I'm just a person too. So whatever questions you have, I'm happy to answer those questions. All right. So I'm going to stop the administrative stuff now for a second. Any final questions on the administrative stuff? And I'm sure there's lots of detailed stuff that you guys have that you want to ask. But if it's detailed, we can deal with that later. And the exam stuff will come into focus a little bit more as we go through.
I'm not sure if this is an administrative question, but would you recommend any additional resources other than what's, linked to in the syllabus, for extra studying?
That's a great question. I'll have to think about that. I mean, there's particularly for MATLAB stuff, we'll kind of give you some indications about some things that'll help you with MATLAB.
Okay.
So you can see that. But it's a good question. One thing I guess I did want to say before I did move on, one thing that I forgot, and I have screwed up my computer here. Let me see.
I do have a question. I know you didn't want to ask questions about tests, but as a general, will the tests be about coding knowledge or just math ability?
That's a great question, actually. We'll talk. I'll give you a practice exam before the first one. All right, so you can see what it looks like. That's the best way to know. But in general, no, it will not be about coding.
Okay, thank you.
The thing to bear in mind is, again, the intention is that the exam should be like the kind of thing you would sit down with a paper and pencil to do in class. So I won't ask you to do code at all, right? So it'll just be sort of math concepts. The projects, so one reason, again, back to the syllabus, if you look at it, there's 3 exams and 2 projects. The 2 projects are weighted the same as the exams. Those projects will assess your knowledge on coding, right? So we'll talk about that. We're gonna be learning MATLAB a little bit as we go through. One thing I did want to point out, the homework is approximately weekly, okay? Homework is approximately weekly, and we're gonna post a video on this, but the way I do it is the homework itself can be done in MATLAB, okay? In every case. And so what that means is you'll see a problem. I'll put this in learner preview here. So the question I'm asking here, what is X if 2 + 2 = X, right? So what I do is I put in that the answer is 4, and I hit submit, and it should tell me that I am correct. If you've done that, you just got all the points for that problem, all right? So in this case, you're gonna be learning so what this does is it evaluates the MATLAB code in the browser. All happens in the browser, so you're good to go, all right? You could basically write stuff in MATLAB and then basically upload it into here, all right? We're gonna talk more about MATLAB on Thursday, and we are going to, I'm gonna upload a video that talks about how to just walks you through an example problem of how to do this later on. All right, but this is the way we're gonna do this moving forward. All right, I used this in 2112 last semester, even before COVID. Students loved it because they got immediate feedback. All right, on whether or not they were correct or not. And in theory, you should be able to get 100 on every homework. All right, because of this. So we'll talk more about that later. The first homework will be posted tomorrow and will be due in 1 week. All right, so the first homework then is due on, I think effectively that makes it the 16th. And then you'll have a homework due on the 23rd and the 30th. All right, so they're approximately weekly, as we said. All right. All right, there'll be more to say about that. I don't want to get too much down that rabbit hole just yet. But the important thing for you is the first homework will come out tomorrow. Okay, and we'll talk more about that on Thursday in class. All right, any last questions on the admin stuff? I know it was a lot of material real quick. All right, then I'm going to move on to some real stuff. Although my first thing is not going to be too much in the way of real stuff. It's going to be a little bit of overview. All right, so we did the syllabus overview, some basic calculus, and then my why so much effing math, all right, question. In other words, why do we make you guys do so much math? So I want to motivate that a little bit here today, because we do make you do a lot of math in ECE, and there's a reason for it. So we're going to talk through that a little bit. And then one thing that's really key is the sine wave. All right, and that's where we're going to start our class, is thinking about sine waves and what that even means. Okay, so some basic calculus. And first of all, but these notes, by the way, are also in that lecture notes module on Canvas, so you'll see that. All right, some things that we expect you to know: derivatives, everything about derivatives. All right, you should know that. Integrals, and I highlighted the ones that are important. Like in calculus 1 and 2, you probably learned all sorts of secants and cotangents and all kinds of weird stuff that honestly no one really uses all that much. The stuff that really matters in an engineering context are the ones that I have up here. So exponentials. So what do I mean by that? If I say e to the at, where a is a constant, you should know what the derivative of that and what the integral of that is. And let me say something here. You're probably used to x, right? Or f of x, like that. We're not going to have, in electrical engineering, we don't typically have a function of x. So let me throw this out. See something. What does x mean physically as a variable? Usually. In physics, what is x usually referred to?
It refers to horizontal distance often.
Yeah, position.
Yeah, position.
Displacement.
Yeah, position, displacement, horizontal. I mean, you guys are all on the right track. In ECE, we're usually talking about f of t. So what does t mean?
Time.
Time.
All right, we're talking about time, right? And so you'll see things usually being a function of time. Okay. So what you get here is we're going to talk a lot about exponentials, sines and cosines, integration by parts, polynomials, and to some extent logs and 1 over x, or maybe I should say 1 over t. Okay. All right. These are the ones you need to know. Don't expect that you need to know secants and all kinds of all the weird stuff that's out there. All right. And what's the integral of inverse sine or inverse cosine? These ones you should know. What's the integral of sine? What's the integral of cosine? What's the derivative of those things? Okay. The first homework will have on it some review of some of the things that you should know. All right. The exponential you're going to find and sine and cosine are wholly critical to electrical and computer engineering because they're key to everything we do. Okay. Even when it doesn't look like they are, they still are, which we'll get into a little bit here today. The other thing is I wrote ODEs, ordinary differential equations. You've taken ordinary differential equations to get into this class. I guess yeah, you've taken ODEs to get into this class. We will review them, and we're going to look at how to solve them and how to apply them again. So there'll be a little bit of review when we talk about ODEs, but we're also going to talk about how to do them numerically, all right, which is important for a lot of problems. All right, so key thing is I'm expecting that you guys know this stuff. All right, now my bigger question, why so much math? Okay, why so much math? All right, and my computer, there we go. All right, I'm gonna give an example. All right, let's say you wanted to build a robot, a good ECE problem, okay? A lot of you guys may have done that already. You may have gone online and gotten something like an Arduino like this, which is a microcontroller. You can take that microcontroller and you could easily, and this is basically from arduino.com. Here's an example of how to build a robot. This is just a screenshot from the page. I could go in there and I could get an Arduino, write some basic code for it, get this thing here called a motor shield, which basically is some electronics that will sit between the microcontroller and this geared motor right here. And if I build if I put the motor and I add a wheel to it and put it on a little frame, I'll build a robot, right? And I write code inside the microcontroller that allows me to guide that robot, okay? Any old Joe on the internet can read this website and put that together and build it. As an engineer, your job is to know not just that I can build that, but how would I build that from scratch? And how do I understand how to really design that thing? All right. And to do that, it's essential that we have math, right? And it's essential that we have things like differential equations and all of that stuff, right? So, and again, this is a problem that is both computer and electrical. And I chose, and actually in the case of a robot, it's electrical, it's computer, it's mechanical. It's all those things, all right? It's hard to get away from that in most applications anymore. All right, but I want to give you an example of why, as a electrical computer engineer, why it is math and what math allows me to do that ultimately sets you apart from the tinkerer online, all right, and allows you to become something that is much more powerful, which is a designer. Okay, so I want to minimize this for a second, and hopefully this is going to work. All right, so what I have here is, this is actually a video that was at, some of you guys may have seen this. This was at Discovery Place here in Charlotte back when you used to be able to go places. What you have is a robot arm, and that robot arm is connected to a Rubik's Cube. All right, and so I'm gonna run that thing here real quick, and you can watch what this guy does. So in particular, what he's about to do is what I want to focus on. All right, which, there we go. All right, at some point it's going to start doing its thing. All right, there it goes. Now it's starting to turn the Rubik's Cube. All right. Now notice what it's doing is it's making these precise 90-degree spins. All right, so I'm going to pause it there for a second. It makes these precise 90-degree spins. Now, to do that is actually not the easiest thing to do in the world, right? If I go back, I had another video, but I think I closed it by accident. Let me see, robot. See if I can, pull this up. Yep, this is what I wanted. Hopefully I don't have to watch a commercial. There we go. All right. Here's an example. All right, so what I want you to, I'm gonna go back here real quick. I want you to watch. Basically what I'm gonna do is this thing's raising this robot arm. What's the difference between the one on the left and the one on the right?
The one on the left kind of bounces a bit.
The one on the left bounces a bit. It is what I call undamped. All right. Now, the one on the right is what you would want it to do. If you had a robot arm, you'd want it to behave like that thing I just showed, where it was making really precise movements. Right. It was making precise 90-degree turns. It wasn't making 92-degree turns. It wasn't making 91-degree turns. It was making 90-degree turns. Like if I want to raise this guy up, right? So in this case, if I want to raise this arm up, I want it to go right to the right spot. I don't want it to go to the right spot, overshoot it, and kind of hang out a little bit, right? If I'm just the guy building a robot with an Arduino, then I may not know how to do that properly, right? To be able to build what I just showed, that sort of precise tools, we need the right mathematical tools to be able to do that. And really, I think ultimately what sets the engineer apart, what I learned in school, back when I was in school, what we talked about was the usefulness and importance of models. When I say models, what I mean by that is that we have a mathematical formulation that allows us to really use this viewpoint. And we're going to use this viewpoint everywhere throughout this semester. And really, you're going to see it in every class kind of beyond this, which is to say that ultimately, whether I'm building a circuit or whether I'm building a robot or whether I'm building a bridge, whatever I'm building, I can think of that thing that I'm building as this generic system. And that system has an input that I'm going to call X of t and an output that I'm going to call Y of t. So one thing that we've learned already is X, in the context of our ECE problems, X of t is going to be our input, all right? And Y is going to be our output. And the of t part, what that means is that it means that the input and the output might change as functions of time, okay? So those inputs and outputs can be anything, right? So in the case of the motor that I showed, so let me, I'll keep that. In the case of, these motors and did I close the other one? I did. In the case of any of these motors, let me ask you guys this. This is outside the scope of the class, but some of you should know this. What kind of motor do I have here typically? Anybody know?
Stepper motor.
All right, I heard stepper motor. That's one possibility. It's not all that common, actually. Let me see if there's some stuff in the chat here too.
Or servo.
Okay, I heard servo motor. All right, and if you're going to use a servo motor, all right, what type of the other term we use for that sometimes is a DC motor. Okay, if I say a DC motor, what does that mean? Do you think?
It is usually a motor that operates in one direction of rotation using DC current.
Well, it can operate in two directions. All right, but I apply a DC voltage to it. All right, and that motor could be a brushless motor. I saw somebody write brushless in the chat. That's one possibility. That's a type of DC motor. All right, but a DC motor basically implies that I apply a DC current or a DC voltage to that motor, and we could talk all day long about the physics of that machine or that motor. But basically, if I apply as my input a DC voltage, what do you think is the output? If I take this, if I want to make this mathematical model of a motor, I'll put in input. My input will be a voltage that I apply at the terminals of the motor. What's the output?
Torque.
Could be torque. That's one possibility. Speed is one. Position is one. So like in the case of what I just showed here with this video, right? What was the actual output? So there's a voltage that's applied to the motor, but what's the actual output that I'm monitoring?
Position.
Position, okay? And in this case, position is actually the angle of it, right? In the little robot that I gave there before, I might want to move that guy 90 degrees, right? And so not 91 degrees, not 92 degrees, right? I want to move him 90 degrees, all right? So my input is a voltage, and my output is a position. Now, what voltage do I apply to get that output, to get 90 degrees? Well, I don't know, right? What the math allows me to do, if I have a good model for this system, then I can know, well, if I put 1 volt here, what angle am I going to get here, all right? And this becomes really important because if you look at this example of what I did, and I keep going back and forth here, all right, if I use this example of what I showed here, we look at the one on the left, that one on the left has that motion like that. That's undesirable. I can stop that from happening. Clearly, this is the same robot here, but it's the overall system is designed better. So what had to have happened in that particular case is that somebody had a good model for the system and determined exactly what that input needed to be to get the output to go straight to whatever final position I wanted without bouncing around like that. As an engineer, right? I mean, we often say, well, that's good enough, right? And the hobby stuff that we talked about, if I just want to make a robot, move, down the hallway or something like that, strapping together, a piece of plexiglass and some wheels and a microcontroller and doing something really simple can be really rewarding. But as an engineer, ultimately our goal is to be able to figure out how to design the system so that I get it to do exactly what I want it to do, or at least as close to what I want it to do as is possible. And there's no way of doing that without a good model. And when I say model, what I mean is a mathematical model for what's happening inside of that system that I want to control. Right? So like what I've written here, it says, essentially the model allows us to answer this question or questions like this. If I apply a voltage, what do I expect the system to do? If it doesn't do something, how do I fix it? Sometimes what I find out is that my model is incomplete. Okay, we'll look at some examples of that later in the semester. But plenty of times I've blown up a circuit. And the reason I blew up the circuit is because I didn't have the right model, right? If you think about in the real world, what do I have? I have a robot, it's got a motor, it's got a microcontroller. That's not a model. That's just the stuff. The question is, how do I develop equations and things like that I can use to say, what is that microcontroller doing? What is that motor doing? Okay. And so just real quick, we're going to kind of think this through real quick. So this is a model for a DC motor. And that's what, you guys said servo motor and things like that. That's what this thing is. And I don't want to get into all the physics of it, but essentially, if you look at what's inside of a motor, I apply it. It has an electrical circuit model that looks something like this. All right. So what I do is so you would apply a voltage here. So I apply a voltage here. All right. And the current flows. And inside of this guy is this really weird thing that is going to be a voltage source that depends on speed. All right. So in other words, if the motor moves faster, then the voltage here gets bigger. All right. We don't need to get too lost in that. Let's just think of this guy as, and so I wrote omega here. Omega means speed. So what's the model that I have here? Well, VA is the voltage that I apply. So I would say VA of T is the voltage I apply, right? And then what would be how would I figure out the current that's flowing in this thing?
Wouldn't it be VA divided by the resistance?
Well, I've got an inductor in here too, right?
Right, so you have to find the equivalent resistance of the inductor.
Well, you're jumping one step ahead of me, Nathan, which is to say, if I get, you're talking about impedances and such, right? So if I just start at IA times RA, right, Ohm's law, and then I can say LA DIA by DT. Wow, that was weird. DIA by DT plus whatever that voltage is that depends on speed. So what did I just get? I got a differential equation. All right, that's never fun to use. But that differential equation ultimately tells me how I can get from the voltage that I apply, that's VA, to somehow to the speed of the machine. Okay? Now, again, it's not a physics class, it's not a circuits class. Important thing is I take this model and I have to pair it somehow with a model for the mechanical system, right? So I apply a voltage, a current flows into the machine. And then over here, I have a mechanical system. So what I've written here is the T's here. What do you think my T stands for in my mechanical system?
Torque?
Torque, yeah. All right, torque. And, you know, just to make things simple, that's like force, right? You guys have seen that in physics. So if I want to figure out what's the relationship between force and, let's say, speed. What is the relationship between force and speed? If I asked you to tell me what's the relationship between force and speed, what would it be?
Force causes acceleration through F equals ma, and then that acceleration causes speed or velocity.
That is exactly what I was looking for. Yeah. So whose law is that, and which one?
Newton's second law.
Newton's second law. All right. So basically, force equals mass times acceleration, or dv by dt. All right. And you say, well, what's the sum of the forces applied to this thing? Well, I can do a torque version of this, a rotational version of it, and I could say, well, the torque equals the moment of inertia times d omega by dt. All right. We don't need to get down into those weeds, but essentially, I can make this model, and you can see a couple of things that this model, from a voltage to let's say a speed of the machine. So it depends on things like the resistance, the inductance. It's going to depend on things like the mass or the moment of inertia, right? But I can build up a whole model for this thing. And ultimately, what do I do with that model? Well, what I do is I ultimately build up a system that can be shown graphically like this. All right. What this is something called a block diagram. All right. And what I have here is it's saying I have some sort of a thing I call a current controller. That current controller sends its output to something called a power converter. And that thing called a power converter sends an output, which is a voltage, into a DC motor. Okay. And the load can basically be, I don't know, a wheel that's moving along a surface or something like that. And what I do is I measure maybe what the position or what the speed is, and I feed that back, and I then have a control system that determines exactly what voltage I should apply to this motor to get it to do what I want it to do. All right. To do that, I need a mathematical model. All right. So there's a lot of Greek and craziness going on in this equation, but it basically tells me omega is the speed of the motor. V sub A is the voltage that I apply going in. All right. So again, there's a lot of variables here. So it's K sub M, and so K sub M is what I call a motor parameter. So it's something I can look on a data sheet. R sub A is a parameter. It's a resistance. L sub A is a parameter. It's an inductance. Anybody know? So I wrote out what effectively amounts to differential equations here, right? I have an input that is a voltage. I have an output that is a speed. So I'm going to ask you guys, if I have an equation like this, which has S's in it, and I started somehow from differential equations, where did these S's come from? What is that?
Are they constants?
What's that?
Are they constants?
They're not constants, they're variables. Let me open up the chat here. Okay, I see Laplace.
Is it speed?
Is it from the Laplace transforms?
Yes, it is from the Laplace transform. That's right. Now, I don't expect you to fully remember that, but you should have seen Laplace transform in differential equations, right? That Laplace transform is actually a useful tool because it allows me to develop this model that tells me ultimately how is a motor how is its speed going to respond to a particular voltage that I put in there. And that allows me to go into a computer and write the code that I need to properly get this motor to do what I want it to do. And when it doesn't do what I wanted it to do, I have a model that I can go back to and I can look at and I can think about to kind of figure out how do I need to tweak and change the code to get it to do what I want it to do. All right, so the reason why I say this is important is to be able to truly design anything, I have to have a model, right? That's what sets you apart from the guy who basically sits down and builds these components. There's nothing wrong with that. That's a fun thing to do, right? And it's a good place to start. But in college now, we want to move on from that. We want to say, okay, well, how do I build this stuff? How do I think about this stuff in such a way that I can actually truly design it and say, how do I make it do exactly what I want it to do, or at least really close to what I want it to do? That's what engineering is, in my view. And to be able to make that work, we need to have the mathematical tools in place to be able to do it, okay? All right, I'm gonna skip over that slide for a second, just in the interest of time. So we got about 15 minutes left here. So I wanna really kind of get into the main content here a little bit, which is, hopefully you get the idea. And we're gonna use plenty of examples like this one, throughout the semester of how is it, in other words, why do we do this? I don't like math. I mean, I like math, kind of, right? But I don't like doing math for the sake of doing math. Very few people do. Some people do. But if you're an engineer, my view is that engineers solve problems, right? And so our goal is to use the math to solve a problem. And so we'll be focused a lot on examples like this to kind of motivate ourselves to think about, why we need the math that we do, okay? So, important thing here today, one of the first critical tools, I've already started talking about things that are a function of time. All right, and so the first signal we're going to talk about a lot. The first thing that I just used a term there, I just used the term signal. All right, you're going to hear that term a lot in electrical and computer engineering. A signal is just a thing that happens in the real world. So when I say I have X of t, all right, that is a signal. It could be a voltage, a current. It's something that evolves over time. And one of the most common types of signals we have is the sine wave. All right, and there's many real world examples of that. So we have audio signals, power waveforms, radio waveforms. All of those are sine waves. They are sinusoidal functions of time. All right, so when I say a sine wave, my definition of that is a sinusoidal function of time. So if you look at the voltage coming out of the wall socket, it's a sine wave. All right, at 60 hertz. Radio is at a high frequency. Audio is maybe around 400 hertz or something like that. All right, and so a couple of things that I want to look at here. All right, the sine function, right? You guys dealt with things in calculus like sine of theta or sine of x. Again, as I said, we don't really talk about functions of x or functions of theta. We might from time to time. But in general, in electrical and computer engineering, we're talking about things that are a function of time. Right? By definition, the sine function or the cosine function is basically periodic in 360 degrees or 2 pi radians. Now, I'll move back and forth a little bit between radians and degrees, but I'm primarily going to focus on degrees. All right? Because if you talk to a real practicing engineer, they will use degrees. They will not use radians, okay? I'll use them both a little bit, but I primarily will focus on degrees, just so you know, all right? When I talk about a sine wave, though, it's a function of time and not angle. It is still periodic in 360 degrees, but what we do is we say, if you look at the graph over here on the right, if I look at it as I change from this picture to this picture, the thing that's changing here is the x-axis. It's written as theta here and omega t here. So what does that mean? If I say, if it's theta equals omega t, what does that mean? What does it mean that theta, the angle, equals omega times t?
Is it equal to the angular frequency times time?
Yeah, which basically, ultimately what that really means is that the angle is advancing as a function of time. And how fast that angle is advancing is a function of omega, which is this angular frequency. All right. Now you're going to play with this a lot in the first homework, right? Because we got to get familiar with this idea. It's incredibly crucial to everything we do. Because even waveforms that don't look like sine waves are actually sine waves, as we'll learn. Okay. So a couple of important things. This waveform is periodic. Okay. Its period is, and these are the important things that we look at when we look at a sine wave, right? We say that it has a period t, a frequency f in hertz, and an angular frequency in radians per second. And I've put here all of the relationships for that. All right. So the period is capital T. So capital T is our period, right? 1 over that is our frequency in hertz. That's the number we typically use. All right. Engineers typically talk about the frequency in hertz. So I said our power wave is 60 hertz. If I have a power waveform that has a frequency of 60 hertz, what does that mean to say that it has, just in words, what does that mean that its frequency is 60 hertz?
60 times a second?
It repeats 60 times every second. In other words, we go through one period, right? So the period here, I'm going to be careful about, I'm going to do it on this slide. Here's our period, t, all right? We go through one period of that waveform in a time period t. And so I'm going to say x of t equals x of t plus capital T. In other words, the value of the waveform one period from now is equal to what it is right now. So in other words, the value right here at the peak is equal to the value at the next peak, right? The value here is equal to the value here, right? That is the definition of a periodic waveform. And a sine wave is a special case of a periodic waveform. We're going to talk a lot about periodic waveforms. We have ways of taking any periodic waveforms and turning them into sine waves, as we'll see. All right. So we'll talk a little bit more. I'm going to wrap up with a couple more thoughts on that. It's a very simple concept. There's not a whole lot more to say about it. We'll have a little bit more to say next time. What I wanted to do here in the last, I don't know, let's say five-ish minutes, I guess, here. Sonny, are you on? Or did I scare you away? Sonny, can you share your screen?
Yeah, I'm here. Sorry about that.
Yeah, can you share your screen?
Yeah, sure thing.
All right. What Sonny is doing, if you can see my webcam there. All right, let me see. I don't know if you, those of you who can, I don't know where I appear in the webcam if I do to you guys, but I have, what he has connected is something called a software-defined radio that he has connected to his computer. So Sonny, can you go ahead and just, well, let me talk about this. This guy's, I got a piece of hardware right here. All right, this hardware has in it basically some electronics. It's USB connected to your computer. And what Sonny's got here on his screen, Sonny's one of my grad students. I asked him to set this up, and I don't know how to make that go away. But what you guys can see here, hopefully, is it has this thing over here called a source. And that output, you basically, what I see is the source outputs something over to a low pass filter. And then it goes over to an audio sync. All right, so it follows through a bunch of blocks. What he's built there using effectively what is this piece of hardware that I'm holding up, which I think I'm holding up on the webcam. What he's doing is he's built an FM radio receiver. All right. So Sonny, can you go ahead and run that? All right. Is the audio working?
Yeah. You used to be able to hear the noise. The noise doesn't come through anymore, but if I tune it to a radio station, you'll hear it.
Okay.
AC/DC hasn't actually been with the band in quite
All
some
right.
time.
There
He
we go.
essentially resigned.
I don't know how loud that is for you, but
Yeah.
Sounded.
All right. Go ahead and tune it to somewhere else there for a second. All right. Perfect. All right. What he has up on the screen, can you move that to the side real quick, Sonny, the FFT?
Yep.
So he's got a block there that says, I've got my mouse over it here, WX, well, I'm looking at my own mouse, I guess, WX GUI FFT sync there. What he's doing is, you can bring that FFT up. You may have heard that term before. What it means is fast Fourier transform. If you look at that graph, can you make that graph bigger, Sonny?
Actually, it does not scale any bigger, I don't
Okay.
think. I
All
can
right.
widen it a little bit, though.
That's good. That's good. So if you look at the x-axis there, what you see is the x-axis runs from 90 megahertz on the far left to 110 megahertz on the far right. Right? Now, it says on the y-axis, it says power in something called dB, which is decibels. We'll talk about that later. All right? What do you think we're looking at there? Anybody have any ideas what it is? I guess we're looking at an FFT, but what do you think it means for, let's say, if you look at right around 100 megahertz there, right in the middle of his screen, you see that there's something jumping from about -60 up to about -20, right? What is that thing? What is that jump? So somebody wrote in the chat, frequency response of the receiver, right? What this thing is, what this FFT tells me is that there is a sine wave that this radio is picking up that is really close to 100 megahertz, right? So this thing is telling me what are the frequencies that you can see. Yeah, so I see somebody wrote in the chat how strong the signal is. What it's telling me is how strong the signal is at 100 megahertz, okay? And what you can do, if you think about it, this is what is transmitted over the air is a sine wave. And that sine wave is ultimately, it is frequency modulated, meaning that its frequency is somehow varied by some audio signal. So when we were listening to 99.7 right there, right, and they're talking about AC/DC, whatever that voice is, basically gets transferred onto the frequency of this 100 megahertz waveform, transmitted over the airwaves and picked up by this radio. All right, this is an example we're going to deal with a lot throughout the semester, but radio is one common place where, sine waves, occur all the time. And one of the things that we're going to do eventually in your projects is you're going to develop something like this, where you take FFTs in real time. All right. And the applications should become pretty clear as we go through this, and we're going to deal with a lot of applications like this. But the sine wave ultimately is one of our key elements. So Sonny, thank you. I'm going to stop your share. So there may be some questions about that kind of stuff, as we go through the semester. We're going to talk a little bit more about the sine wave at the beginning of class on Thursday, but I wanted to motivate it today. The whole idea, if we take nothing away from what we just talked about, sine waves are really critical, okay? If I look at voltages in a power grid, currents in a power grid, if I look at the waveforms that we see, audio waveforms or radio waveforms like we just talked about, they're all sinusoidal, okay? And we're going to talk a little bit more about, this idea here. There you go. What we're going to see here is we're going to talk more about these relationships between these kind of key parameters, the frequencies, the amplitudes. So I didn't talk about the amplitude, but essentially, I guess I outlined here, what the three things are that we care about. So somebody talked about, when I showed Sonny showed that picture of the FFT, the height, somebody said the height was the signal strength. That's the amplitude, right? How big the waveform is, all right? So in words, the way I think about these key parameters, I talk about how fast something varies, which is its frequency, its period, or its angular frequency, right? How big it is, meaning its amplitude, and then how offset it is from being a cosine is represented by something called the phase or phi. All right, we're going to talk more about that on Thursday. We don't have time to talk about that today, but you know, the key thing is when you were looking at that signal strength, right, which is what somebody said on that FFT, what you were looking at is ultimately how big, what the amplitude was. All right, frequency is how fast we're varying. All right, so again, we'll have a little more to say about that, but this sine wave thing is really key, because what we're going to find ultimately is even if I have something called a square wave, I can think of it as a sum of sine waves. So one thing I skipped over previously was I talked about this thing here called an H bridge. All right, I didn't talk about it, I skipped over it. But if you've ever built a motor or done anything like that, what you find is that you have, if you had a microcontroller driving a motor, usually you have something called an H bridge that connects between the microcontroller and the motor. And what you do is you apply a voltage to the motor that looks like this guy. All right, it basically goes up to a particular value, then goes down, then goes up to a particular value, then goes down. It just repeats like that. What kind of wave is that? Anybody know? My last question.
Square wave?
Yeah,
Square
square
wave.
wave.
Square wave. That square wave is a sum of sine waves. In other words, many, many sine waves add up to create that square wave. And if I understand that, I can understand, again, mathematically and modeling wise, why a square wave looks like a sum of sine waves, and how ultimately that becomes really useful at driving something called a DC motor, all right, which we'll deal with those kinds of concepts as we go throughout. All right, so that's it for today. I wanted to, like I said, introduce you guys to the class and the concepts of the class. You know, there'll be lots of stuff that we'll talk about and get into more detail about. There were a couple of questions that came up throughout. I will be taking this recording and I will post it to the Canvas page so you guys can look at it afterwards. We'll go from there. All right, if you have any other questions, I will leave. I'm going to stop the recording, but I'll stay here for another 5-10 minutes, and you guys can ask me questions if you got them.